Hi, my name is Bruce Jakosky. I'm from the University of Colorado in Boulder in the United States. I'm the principal investigator on the Maven mission. That's the Mars Atmosphere and Volatile Evolution mission. It's a spacecraft that we've sent to Mars. It's currently orbiting Mars and sending us back data. I want to tell you a little bit about what the Maven mission is about and how it fits into the broader program of Mars exploration. At a very narrow level, the Maven mission is about trying to understand the nature of the Mars upper atmosphere, how the solar wind and energy from the sun hits the atmosphere, how it controls the composition, structure, and behavior of the top part of the atmosphere. What we're trying to do is to learn about how this leads to escape of the atmosphere to space. We're most interested in learning about the history of the atmosphere because we see a lot of evidence that the Mars climate has changed over time. There's a lot of evidence that there's been liquid water on the surface at times in the past, but we don't see any of that today, and we wonder, where did the water go? Where did the carbon dioxide from the early atmosphere go? It may have gone down into the crust, or it may have gone up to the top of the atmosphere and been lost to space. We're studying this top part of the atmosphere as a way of learning about the conduit, the portal, the path that the gas has to take in going from the main atmosphere to space. What we're learning about then is the habitability of Mars, because we're learning about the volatiles, the gas in the atmosphere, how they've changed over time, and how Mars went from a warm, wet environment in ancient times to the cold, dry desert planet that we see today. So in order to understand the top of the Mars atmosphere, we put the spacecraft into an elliptical orbit around Mars. At the lowest point in the orbit, it's about 150 kilometers above the surface. At the highest point, it's over 6,000 kilometers above the surface. That means that every orbit, we go through the entire upper atmosphere. We pass through it and can make measurements in situ, at the location of the spacecraft. And then from the highest altitudes, we can look down and see the whole planet in front of us and make global scale measurements. This lets us really understand what's going on. We have 9 scientific instruments on the Maven spacecraft. They're designed to let us understand these processes that relate to the upper atmosphere. We have several instruments that measure the energy coming in from the sun, since that's what drives the processes in the upper atmosphere and leads to escape. We need to know the energy input. It comes in the form of extreme ultraviolet radiation. It's a very short wavelength light. And then solar storm events and the solar wind. We measure each one of these as they come and hit Mars, and then we measure the response of the Mars atmosphere and upper atmosphere to this. We see it changing from one orbit to the next and over time as the energy inputs change. And we see how it leads to escape of the atmosphere to space. It gets stripped out the top of the atmosphere and is lost. The rates of escape today are very small. That is, we're not losing much atmosphere today, but we can understand the processes that are operating and learn how to extrapolate those processes back in time to how they would have operated 4 billion years ago when the sun was more intense, when the solar wind was more intense. This lets us put together a complete picture of the evolution of the upper atmosphere. Right now, Maven has been in orbit around Mars for about 6 months. It took us 2 months to commission the spacecraft, get into our science mapping orbit, deploy the booms, make sure all the instruments were operating, and now we've been taking data for about 4 months. During those 4 months, we survived the passage of a comet that had a close approach to Mars, and we made observations of the aftermath of the comet. What happened when all the debris from the comet hit the Mars upper atmosphere? In that, we discovered a new metallic ion layer in the ionosphere that was created by the dust from the comet. Later, we've also discovered a cloud of dust in orbital altitudes, at orbital altitudes surrounding Mars, dust that was not expected, and we don't know where it comes from. We've also discovered a diffuse aurora that is present, that is the aftermath of a solar storm event. A solar storm sent a tremendous flurry of high-energy electrons into Mars, and those electrons hit the atmosphere and triggered an aurora. That's the first time this has been detected at Mars. We've been making measurements pretty continuously for those 4 months, and we're seeing variability in the upper atmosphere. We're determining the composition, and we're seeing how ions in the upper atmosphere get energized, how they get accelerated to escape speeds and are lost from the planet. We don't have an answer today as to how much gas has been lost through time, but that's what we're building toward. By the end of our 1 Earth year primary mission, we should have enough measurements under enough different conditions that we should be able to get a good estimate of how gas is being lost today and of how it has been lost over 4 billion years, and then a good estimate of how much gas Mars used to have in its atmosphere. What we're learning about then is the nature of what makes a planet habitable. What made Mars change from a habitable environment early on to the cold, dry desert planet we see today. But this is just one program, one project in a larger program. Maven is one of many Mars missions. We're currently flying several and have more in the planning stages. And these missions are aimed largely at understanding how the planet as a whole works and whether there could ever have been life on Mars. So in another decade, we hope to have an answer to that question.